specific potentials. So it will be our special speaker today. So David was not taking the course, but he volunteered to make presentation. So if he performs better than anyone else, it means that there was no reason to give the course, and anyone can present it right away.
He's a credit student, right?
Okay.
So we were looking at thin film semiconductors. So what we were modeling, we were also modeling on perovskites. And as you look at this is not the best picture, but the blue atoms here are cesiums, the pink ones are bromines, and the brownish colored ones are lead. And then we have ligands attached. We have ethyl ammonium and acetate ligands attached. And we have two different perovskites that we're looking at, and they vary in their layer setup. So they have layers of cesium and bromine and lead and bromine. So for the cesium-rich perovskite, we have 4 layers of the cesium and bromine and 3 layers of the lead. For the lead-rich surface, we have 3 layers of the lead and 2 layers of the cesium. So then the geometries are optimized in VASP using our first equation here. And then the second equation was used to translate the 3D potential to 1D potential. So what we found is for the lead-rich surface, we have our potential energy wells here, and this isn't the best graph. These ones where the lead is. In this graph, the lead is gray. Where the lead is where the deepest wells are. And the cesium wells and the ligand wells are approximately the same level. And then over here we showed that the dynamic effects of the electron position with time. And it starts on the ligands and moves toward the perovskite. For the cesium-rich surface, we also see the deep wells being on the lead atom, or the lead layers, and the ligands and the cesium layers are also similar in size again. And then we also see that in these ones, the potential is the electrons are moving toward the lead wells here. And so the idea is that this would indicate that there's a good chance that these would be photoluminescent, which is what Daniel was working on when the materials we were using were from Daniel's research. And what he was working on was trying to determine some of their photoluminescent properties.
It done? Okay, let's thank David. So anyone wants to challenge David with questions?
Can you explain this contour plot a bit better? Because to me, I don't understand how you can say that it's photoluminescent looking at it.
I did not include it in the presentation or in the paper there, but in Daniel's paper that we got these models from. So it's the cesium. It's actually showing a trap state on these ligands right here in the HOMO form and for the HOMO orbital. So as we look at it, the electrons are moving toward the perovskite surface.
But if it's a trap state, aren't they typically optically inactive?
Yeah.
So then wouldn't that mean that they're not luminescent even if they spatially localize?
Would it be right
Yeah.
to say that you're exploring whether the charge carrier would prefer to move towards?
What's that?
Whether are you going to explore? Are you exploring whether the electron stays inside the slab or moves towards surface?
So what we were exploring was the idea was that it was moving toward the surface here. So these wells are corresponding approximately to these two layers of the lead surface.
So it's still lead surface, not the organic ligands.
Yeah, not the ligands.
Is it good or bad?
That should be good.
Okay.
Very short question. You put it in atomic units. What can you transfer it at least at something which we typically use? Like
So
what exactly these atomic units in lengths mean? Anyone knows?
Ask the class.
Is it a Bohr?
if I'm trying to remember how big the atomic
Yeah, you
unit
already
was.
passed this course. You got the
It actually has a physical meaning, and he was giving
Yeah.
you a hint. So looks like people should take your course, right? At least to answer this question. Although I'm not sure that everyone knows, but I just suppose.
I remember calculating it when me and Daniel were first sitting down, but I do not remember.
What is bigger, angstrom or atomic unit of length?
Angstrom.
Bigger.
Yeah.
How much?
A little more than double if I remember.
It's a Bohr radius of the first electron. Bohr radius, which is actually the distance of electron from the nuclear at the first orbit, which is around half of angstrom, if you put it in the units.
Good.
Yeah, but
Good.
the physical meaning of your atomic units, in length atomic units, right, that it's a Bohr radius.
Okay.
More questions? If no, let's thank David once again.